All right. So if you recall, in the last lecture, we talked about optimization and we talked about Fisher scoring. Which is adapted from Newton-Raphson. From Newton-Raphson to maximize the log likelihood, the L function. That's our goal. So in particular, our goal is to find the MLE, maximum likelihood estimators, by maximizing the log likelihood function of the beta parameter over possible beta vectors in the p-dimensional space. So to solve the generalized linear model problem. And we study the generalized linear model problem under exponential family for our random structure. Okay, so now let's first need to write out what is the form of the log likelihood for exponential family. Okay, recall that we have yi independently following exponential family with location parameter theta I and scale parameter phi. So not every distribution needs two parameters because, for example, the Bernoulli, Poisson, they only need one parameter, and that's the location parameter. So the location parameter is specific to our response I, but we assume the scale parameter to be the same thing for all i's. This is just for simplicity. Just like in linear model, the error variance sigma square is assumed to be the same, but we have the mu I, the mean of the normal distribution, to be specific to response I, and that mu I is depending on the covariance xi, observation I. So here we have assumed this theta I to be specific to response I. Then for this distribution, we specified its probability density function in a previous lecture. So I'll directly write down the log likelihood. So from here, the log likelihood of beta takes the form that is the summation over my observations, I from 1 to n. And in the sum, I will get two terms. One is yi times theta I minus b theta I, right, over ai phi plus a c function of yi and phi. That's a log likelihood. And now because of our systematic structure, so this comes from our random structure. Let me just be a little specific so you know the connection. Given the random structure, we write down the log likelihood, but we don't see beta appear yet. The reason is that the parameter relation is only based on exponential family. We didn't introduce the systematic structure yet. So from the systematic structure, under the canonical link function, that's another thing, with canonical link function, what we actually have is theta I is specified to be the linear predictor. We call that eta I, and is xi transpose beta. So this is how we can introduce beta into the log likelihood. Then the log likelihood becomes, so, for these two terms, theta I, we were going to replace them by xi transpose beta. Okay, so basically, I'll just skip the other terms, but write what it should be changed. Yi times xi transpose beta minus b of xi transpose beta. And the other terms stays the same as left. Okay, then to use Fisher scoring, recall what it is, right? Fisher scoring, this is what we talked about last time. It's an iterative algorithm to iteratively update our parameter, the beta. So in the let's say the k parameter as parameter update, we basically have beta. I remember I used this one, t+1 will be updated as in the t iteration, beta t, the current value, plus the Fisher information, which is a matrix at the current value. Take the inverse of the Fisher information. So this is p by p, this is p by 1, this is p by 1, times the scoring function at beta t. Okay, now let me ask you this question to help you engage. How do we define scoring function? The scoring function, I can give you the hint that it's a vector, p by 1. What is the definition of a scoring function? Any volunteer on the Zoom? You can unmute yourself to speak.
Isn't it just the gradient
Gradient of what?
of beta?
Gradient of beta. What is the function? Gradient of what function? Yes. You need to define the function and then it's gradient, right?
Is it of the...
It's the thing we want to maximize.
log likelihood, I see.
Log likelihood, yes. Good, thank you for the answer. And then anybody else want to volunteer to talk about Fisher information? What is it? So just recall, S of beta, the score function. Okay, score function is defined as the gradient of log likelihood at this beta t. And then we have Fisher information, which gives the name Fisher scoring. It's based on these two terms, Fisher information. What is the definition of Fisher information? Any volunteer?
Isn't the expectation of the square of the score function?
Yeah, you can define in two ways. So the way we introduced in the class last time is the expectation of the negative of the Hessian matrix. That's the Hessian matrix of this log likelihood at, sorry, it's this one. Sorry, Hessian matrix of log likelihood at beta t. Sorry, messy writing. That's what we introduced. But Chen-Xin give another definition. We can show that this is equal to, it's a not so complicated proof. You can show that it's equal to the expectation of the outer product of the score function. So it's basically S beta t, which is p by 1 times S beta t transpose. This is 1 by p. So then you get a p by p matrix. So we didn't show the equivalence here, but it is something you can show yourself based on this. And the key thing to remember is that the scoring function has expectation at any beta value equal to 0. And this 0 is a p-dimensional 0 vector. So that's something we showed previously. So then you can see to use the Fisher scoring to iteratively update our beta value to hopefully maximize the log likelihood of beta, we need to calculate the score function and the Fisher information. That's the two things we need to calculate. And we need to calculate both score function is a function of beta, Fisher information is a function of beta. As long as we have the function forms, when we do the update, we just plug in the current beta value to find the next beta value, and then put the next beta value into the score function, into the Fisher information to find the next beta value. So that's how the iteration works. So then for today, we are going to derive the score function and Fisher information, and then we'll show you why this iteration would ultimately become an iteratively reweighted least square. So basically it become a least square problem we can solve that in each iteration. And that will give us a way to do the calculation very fast because we already have very good approaches for solving the least square. So basically, even though it's iteration, but in each iteration, it's a closed form. It's a least square solution. Okay, so basically, let's define this log likelihood because it's a summation, right? So let me just call the terms. Let me just call each term as Li. So don't forget that Li is basically a function of beta himself. So basically, I'm just saying that in the summation, I call every term Li. So this is the term contributed by the ith observation to my log likelihood. Okay. I want to make sure that everyone is on the same page about notations before we move on. Okay, so we write L equals to summation of Li, and Li is also a function of beta. All right, so therefore, here the thing is the logic is that to obtain this gradient of log likelihood at beta, which can be essentially written as the summation I from 1 to n, the gradient of Li at beta, okay? And for Li, the ith function term here, we can also write it as what? Where this Li, I just drop beta for notation simplicity. I know it's a function of beta. Is it defined as this column vector, which is partial Li partial beta 1 to partial Li partial beta p. It's a p-dimensional vector gradient. Okay, and for now, let me just make another thing. We assume to maximize this likelihood, we don't worry about phi for now. We assume this phi is fixed. It's just unknown but fixed. So we just worry about the beta because beta is only linked to theta I, the location parameter, not phi. This is similar to when we solved the linear model. When we try to find the beta hat, we didn't worry about sigma squared at that time, right? Remember, we first get the beta hat, we obtain the residuals, and then we use the residuals to find the estimate for sigma squared. So sigma squared was estimated later. For the same reason, we assume that, so in this maximization, we just fix phi without worrying about now, just worry about maximizing beta. Okay, so how do we do this calculation? So therefore, we need this partial Li partial beta j. Okay, so I'm looking at j, which is 1 of 1 to p. I'm looking at this partial derivative. And then I will use the chain rule to kick in because you see here, the likelihood is first defined based on theta I, and theta I is the natural location parameter in my exponential family. So basically, you see the thing is that I have, maybe I can be a little simpler because in this case, I already have theta I equals to this, xi transpose beta. So I skip these steps, I just directly go from here to here. That's what I will do. So then I would write this as chain rule partial Li partial theta I, okay? And partial theta I partial beta j. This is what I will do. And don't forget that we have theta I defined as xi transpose beta. Okay, so by writing out this inner product is j from 1 to p xij times beta j. Okay. Okay. So Therefore, from here to here, let me see if I miss anything. Let's see. I think I probably cannot skip the steps. I apologize for that. Okay, yeah, because I don't think the terms can be canceled in this way. Even though we assume that. Okay, maybe I'll just write the complete form. I apologize for that. So maybe I'll just start from here again. So we'll leave it here because we may come back. But what I want to say here is that if we don't think about the canonical link function, okay, in the most general form, not the canonical link function, in the most general form, what happens is this. Expectation of yi, let me just give you this review, is defined as mu I, right? And from the exponential family property, we know that mu I is b prime theta I. This is what we gave you before. And also, this is the property of exponential family from the random structure. From the systematic structure, we have the link function g of mu I is defined as eta I. Linear predictor is defined as xi transpose beta. Okay, so in the complete sense, if we don't specify eta to be equal to theta I, if we don't make this jump, we need all these things involved. That is, we need theta I, we need mu I. So the relationship is we have theta I in the likelihood, we can link theta I to mu I, and we can link mu I to eta I, and we can link eta I to beta. So that's how we go to get to the chain rule to this case, from theta I to beta. So then if we follow this, what happens is that this partial Li, partial beta, if we follow this whole chain rule, is partial Li, partial theta I, and theta I depends on mu I. And this is not a multivariate function. So mu I scalar, theta I scalar. So it's just d theta I, d mu I. Okay. And then we will link mu I to eta I. Mu I and eta I are also scalar. So it's d mu I, d eta I. Finally, eta I is a scalar, but beta is a vector. So the last step is partial eta I, partial beta j. That's how we can have this full chain rule here. While on the left, I skip the middle steps because I set each theta I to eta I. So I skip the middle steps. But let's just talk about the general form for now. So then to get this gradient, then we will calculate each element specifically. Okay, so let me just move down here. So we will do one term at a time. So recall that Li, if we look at in terms of theta, Li theta I, in the likelihood term, it's basically, let's just write it, yi theta I minus b theta I, ai phi, plus c function yi phi. Okay, so from this term, then we can directly get partial Li, partial theta I is what? Or maybe I should change it to d because theta I is also a scalar. Sorry, yeah, it should be d. So d I Li d theta I is what? I just take derivative of that. This term will be gone. Denominator stays, just the numerator. So it's yi minus b prime theta I, ai phi. That's my first term. Okay, and then the second term, so I have this. The second term I need is d theta I d mu I. How do we go from there? So this is the thing we will use from here, this relationship, the mu I equals b prime theta I. Okay, so from this mu I equals b prime theta I, what I can get is d mu I d theta I. I go from the left side, it's just b double prime, second derivative at theta I. Okay, and then what I need here, I can take the reverse of the two relationship because I want to keep everything in theta I, not mu I. So this will give me d theta I, d mu I is 1 over b double prime theta I. So note that I'm not writing this in terms of mu I, but I'm writing in terms of theta I. So that's why I take this. So we keep this second term and we'll see how things can be canceled in the second term. And for the third term, it's based on this. G mu I equals eta I, this thing. And what we have here. So again, we'll use the same thing. So because G mu I, same trick, equals eta I, if I do d eta I d mu I, it's just give me G prime mu I. Okay, and then I reverse it. It's d mu I d eta I is 1 over G prime mu I. Same thing. So I'm writing this in terms of mu I, not in terms of eta I. Okay, we have 3 terms. Finally, the last term is actually easy. The last term will be based on the fact that eta I is defined as the linear predictor xi transpose beta. And as I said, it can be expressed as j from 1 to p, xij, beta j. So if we extract in this way, then partial eta I, partial beta j, because this is beta is a scalar, this is a vector, so we have this partial. That gave me just xij. So that's the last term I need. Okay, so then we put it together. All these terms we put it together. What do we get? It's just this. So putting things together, we just multiply them up. Partial Li, partial beta j. Turned out to be yi minus b prime theta I, ai phi, okay, times 1 over b double prime theta I, times 1 over g prime mu I, times lastly xij. That's the gradient. And now we can combine some terms. This is also something we talked about when we introduced exponential family. So if we scroll back here, using this exponential family density function, in the formula we give you, we have expectation of yi as b prime theta I. This is what we just used. We also give you the variance formula. Variance of yi is what? If you check the notes, it's actually ai phi times b double prime theta I. This is the variance formula we previously derived using the exponential family. Then you see, if you notice the variance formula, we can scroll down here. This term and this term, they multiply to each other in the denominator. That's just the variance of yi. This is a very useful simplification because we're getting closer to a simpler form. Variance of yi times 1 over times xij. Okay, So that's how we get the score function. Okay. And one more thing, what we could do is that now we have this form. And what we can do is to introduce, how to say it? So we basically want to change it to something we are familiar with, which is related to, okay, how do I say it? So basically what we want to have is, recall that for the linear model, when we have the least square, when we take the likelihood against the beta j, what did we have at that time? It's the thing we want to solve for the beta hat. If we call that, I don't know if I emphasized it enough, but it's called the normal equation. That's how we get a beta hat equals to x transpose x inverse x transpose y. That's the step we took before that. But here, basically, for this gradient, we want to make up a term similar to what we have that. But we just want to find it as a way, write as a way. So we have the, maybe let me just go to one more step in the previous case, right? Maybe instead of just saying. So recall that in the previous case, when we take the log likelihood, in that case, Li, what is the form of that? I think you should be able to recall that. So Li beta in the linear model case, the Li beta is just Yi minus Xi transpose beta squared negative, I should say. It's the negative of this 2 sigma squared plus some constant. Yeah, the constant, I just ignore it. Okay, so in that case, when we take the gradient against beta or partial derivative Li beta j, what do we have in that case? So basically, we can have two cancel each other out, and we have a sigma square here, right? So then we have this what? Yi minus Xi transpose beta, right? 2 times that, and then we have Xij, and that negative sign and this cancel. So we get this. This is the gradient. And that time we just directly set it to 0. We set it to 0 and solve for that. So right now you see that what we have something similar to here. I just want to see your comparison of the two terms. We have Xij and we have Yi minus something. Previously, sigma square is the variance of Yi, and we have variance of Y here. But we have this additional term that bothered us. So therefore, we want to consider this to be some weights. And then we call this a weighted least square problem because we're basically like weighting each Xij by having a weight specific to I. So from here, once you see this similarity, did you see any similarity here? If you do so, then let's move on to see how we are going to further transform the form. So it's something we can solve by weighted least square. So from here, then what we want to do is that we want to further, so from the left, we write down here, we further write partial Li partial beta j, the term we need for our gradient, as this. Yi minus this one, beta hat theta I, is what we call mu I. Don't forget, mu I is just the mean of yi, so we can write as mu I. I know the confusion here is that we have so many parameters, they mean different things. We try to link them together. But hopefully, if I go slowly, it's something you can see how dots are connected. And I have to clarify, everything we're doing right now is to simplify the optimization as something we can solve fast. Otherwise, if we just use brute force optimization, we don't need those nowadays because we have very powerful computer. But I think if we can follow the old wisdom, I would say, to simplify things into something solvable, by hand or by closed form is usually faster and more stable. So that's why I think it's still worth to know. It's something very, I would say, smart that they did in the past. So change b prime theta back to mu I. And what I will also do is that I will multiply g prime mu I in the numerator. So then you can see that the denominator will become variance of yi times g prime mu I squared. So I didn't change anything. So this additional copy of g prime ui is introduced to cancel out the square here. So I changed the denominator from one copy to the square. So it's basically the same thing, times xij. Okay, I didn't change anything, just to add up the terms. And then what I want to call this would be, basically, now I will define a bunch of notations. So before I go there, let's first go to the vector, go to the sum. So then I can say that partial log likelihood, partial beta j. Now we go back to log likelihood, not just the ith term, it's just a summation of this whole thing. I from 1 to m by I minus mu I, g prime mu I over variance of yi g prime mu I squared times xij. Okay, so this is the partial derivative I need in my gradient. Okay, and then you see that if I want to go to the vector form, not just the scalar form, for the vector form, I define the following things. Maybe I'll take another piece of paper. So I will make some definitions here. First of all, I will define this notation. It's a new notation. Y minus mu d eta d mu. So it's just a notation as a whole thing. Don't interpret this as a calculation. This notation is defined just as my numerator. I define it as y1 minus mu1 for the first observation times g prime mu1. Down here, yn minus mu n times g prime mu n. That's the vector. Okay, and I will put this thing as a denominator, the denominator as a weight matrix. As I said, it's a weighted least square. Maybe I should have introduced weighted least square first, but later, after we finish all of this, I will give you the standard weighted least square. So you can see that what we're doing here is just a special case application of weighted least square. The second thing I will introduce is called the weight matrix, W. It's a notation, and I define it to be just a diagonal matrix. It's an n by n diagonal matrix. And this is an n by 1 vector. In the diagonal matrix, each entry on the diagonal is just what we have in the denominator. 1 over variance of y1 g prime mu1 squared. That's the first one. And we have the diagonal 1 over variance of yn g prime mu n squared. That's the last one. And all the off-diagonal terms are 0. This is what we define as the weight matrix. Okay. Finally, let's go back to what we're familiar with, design matrix. So in the design matrix, you recall that n by p design matrix, we can write it in two ways. One way is that we can write it out by row. So we have xi transpose to xn transpose. Each row is the p covariance of the ith observation. Or we can write it out by column, x1 to xp. And each column here is the pth covariant or predictor of my n observations. So please note that here x1 is just the intercept. So I didn't try to differentiate the intercept between intercept and predictors. I keep them all here. But specifically, when we write out xj, it's a column vector. It's basically x1j up to xnj. So these are the notations I want you to be familiar with. And also maybe one more thing I want to add here to simplify the thing is that I can call this first diagonal entry as W1, the last W entry is Wn. So I can also use notation W1 to Wn here. Okay, now you see we can have a much simpler matrix form for this thing, here. So with these matrix notations, this W and X, what I can write here is that maybe what I can write here is to compare the two terms, is that then my partial L partial beta J for this whole thing can be written as xj transpose times the W matrix, the weight matrix, times the vector. The vector is y minus mu d eta d mu. So y explains the denominator, this explains the numerator, and the summation is just the inner product over I. So that's why I'm changing it to this way. So basically it's the inner product of xj, which is n-dimensional, and this thing, which is n-dimensional, that give me the summation across I. But this weight is here to explain the denominator. Is everybody following? Here, how do we go from here to here? So this part comes from xj. This part comes from this vector, and denominator comes from the weight. Okay, then I can further write out my gradient in the matrix form. So everything I'm trying to do here is to get a matrix form. So it's much simpler for us. Just like in the linear model, using the matrix form to solve for least square, it was much simpler for us. So then, finally, so let me assume that you accept this form already. If not, we can go back and revisit the details. But let's say we start from here. Then for the vector form, partial L, or I will just say this, it's just gradient L at beta. This is what? Remember definition, partial L partial beta 1, partial L partial beta j. Okay, the reason I write the inner product in this way is like xj transpose. This becomes what? Xj transpose is 1 by n, wn by n, this is n by 1. Because I could also write as the transpose of this one times xj. But the reason I write it this way is that I want to stack xj by row. That's the reason. So therefore, you see what happens here is that only the xj is related to j, the jth predictor. W is not specific to J. This is not specific to J. If you look at definition here, this is including just the Y1 to Yn, mu1 to mu(n). That's not specific to beta J or feature J, predictor J. So therefore, from this line to this line, I just need to stack my xj. It becomes just x1 transpose to beta p, xp transpose. I stack them times W times Y minus mu d eta d mu. Okay, then what is this? Recall that I said design matrix is x1 to xp. Now I'm having x1 transpose xp transpose stacked by row. This is exactly x transpose, right? So I get x transpose W Y minus mu d eta d mu. And don't forget, the last term is its own thing. That's it. Okay, that's my score function. This is my score function. Yeah. Score function at beta. And we have a very simple matrix form. Any questions? All right. If there are no more questions, let's move on to Fisher information. Next, Fisher information. And because the Fisher information will involve second derivatives, so we would need to calculate second partial derivatives of our ith entry in the log likelihood against two beta j's, partial beta j, partial beta k. So we need this because this Hessian matrix, so this Fisher version would need a Hessian matrix, and Hessian matrix, this is its, square. This is its jkth entry in the Hessian matrix, and this is p by p. Okay, now how do we go from here? So for this, let's go back to revisit what we have here. And so we just go one more step from, let's just go one more step from this Li right here, right, to go one more step to take another derivative. So now we have introduced the convenient notation of Wi as this. Now we want to use that in our formula to simplify our notation, just to simplify notation. So using the notation we define on the next page, this can be written as yi minus mu I times g prime mu I, this stays, but the denominator, now we change it to wi. That's how we call the wi, right? And then we have what? Xij. So we can regard this as the partial Li partial beta j to start with, and we then take another derivative against beta k. So that's what we'll do. So let me just copy things down here. It will be partial beta k of what we have here. Yi minus mu I, g prime mu I, wi, xij. So starting from there, we take the partial derivative against beta k. And then you can imagine what will be involved again. So one is that you will, so basically we will use the, again, we will use the derivative differentiation for a product to separate two things. So what will happen here is that we will try to recycle some of the results we used. So we first put the derivative on the second part, keep this as is, keep the first term as is. Yi minus mu I partial beta k g prime mu I times wi xij. Okay, plus we put the partial derivative on the first term. Partial beta k yi minus mu I, this term times what's left, g prime mu I wi xij. Okay, we have these two terms. And now what we can do is to go to Fisher information. Now you can see why changing this to expectation is so much easier for simplification. So because Fisher information would just need expectation of Hessian, not Hessian. Then let's see what happens if I put expectation around. So what happens if I put expectation around this Li partial beta j, partial beta k? If I do this, then I put expectation around each thing. So first of all, now you can see why I want to separate the terms. What happens to the first term? The first term would just give me expectation yi minus mu I, because recall that when we set expectation, we need to know the random variables. And the random variables here is just yi. Nothing else is random. So that makes it easy for us, because for the first term, I just put expectation around that. And for the remaining term, they stay. They stay here. But what's good for us is that this term is actually 0, because mu I is defined as the expectation of yi. So it's 0. So I have 0 for the first term. Then I just put the second term, put expectation around the second term. For the second term, what happens here in here? Maybe we should first do the differentiation first. Okay, I put everything in expectation, but let's do the first differentiation. Yi is gone. See, because yi has nothing to do with beta k. So when we do the differentiation, I'm left with partial mu I partial beta k, right? Times g prime mu I wi weight I xij. Okay. And I just need to get rid of the expectation, because it has nothing to do, there's no randomness left in the second term. Everything is just a constant. So I keep everything minus partial mu I partial beta k g mu I wi xij. Then I'm only left to do this partial derivative. And we can see that because we can do this right here. So I can do this right here. So partial mu I partial beta k, we use the chain rule again, which is, if you recall, systematic structure will link us from mu I to eta I to beta k. Eta is the linear predictor. So we do that as well. D mu I, D eta I. They are both scalar. Finally, partial eta I, partial beta k. Recall that in the last page, we derived this. Recall here, d mu I, d eta I is 1 over g prime mu I. We borrow that result here. 1 over g prime mu I. Eta I, beta k, we did it here. Beta, this one. But here's beta j, so it's xij. But if it's beta k, it should be xik. Okay, so then with all of this, we put it back. And then you can see we have some nice cancellation. So I have minus 0 is gone. I put it here. So I get 1 over g prime mu I xik g prime mu I wi xij, right? So this term, they got canceled. So I'm left with minus xik wi xij, which is a very simple form for the jkth entry, actually in my negative Fisher information. So because like you see that since, which is what? Which is, I'll just write it, it's the jk entry of negative Fisher information, because Fisher information should have a negative sign here. All right, so then what is Fisher information? So you see that I need Fisher information to be P by P, but this is the jkth entry of that, and they are rescaled by the ith weight. I can give you the result. That is, finally, then the Fisher information, put everything into a matrix form, is just X transpose W X. Okay, so X is P by N, Wn by N, Xn by P, and we get this matrix. So if you want to verify this yourself, you are very welcome to do so. Oh, one more thing. Sorry, I forgot to say. Yeah, before I jump to this conclusion, I didn't give you this summation yet. That's my bad. So from here, just give me one more step. I think that will be clearer. So the expectation of this partial square L, not just Li, partial beta J, partial beta K. Sorry, this is wrong. This term is the ijth entry of Fisher information, negative Fisher information. It's not Li. It's just this is just the ith term. I need to take a sum over that. So I need to sum it over, and this will give me sum I from 1 to m xik wi xij. So I will get this, and then I can tell you that because the sum can be interpreted as an inner product, I can write this as negative xj transpose wxk. Yeah, so the jth column, kth column of the design matrix, I'm taking their inner product. For each entry, I reweighted by wi. That's their correspondence. Then you see that I can go from here, and this is the jkth entry of negative Fisher information. So I have negative sign here, negative sign here. I can cancel them both. That gave me to this. So finally, I go from here to here. So I stack the jth row across the jth predictors, and here I stack the kth column by column to get a design matrix. So that's why I have X transpose on the left side, X on the right hand side. So I'm stacking rows here, I'm stacking columns here. That's how I get the matrix form. So if this is something not so familiar with you, I think it's mostly because of the familiarity with linear algebra. Probably that varies from student to student, but I hope that it makes intuitive sense to you. And also, I think linear algebra is a very useful tool to simplify our notation and derivation. So that's where we are. All right, after so many steps, finally, let's do Fisher scoring. So come back to here. We have this, and then let's just do the iteration. So iteration will be the current value plus inverse of Fisher information times the score function. So finally, we have beta t plus 1 equals beta t plus inverse of Fisher information. Let me ask you one question. As beta t, I'm just writing this out. I'll do the replacement of our result. Let me ask you, if I want to change this beta to beta t to indicate the tth value for beta, where should I put the t on the right hand side? Because if I have a t on the left hand side, I need to have on the right hand side. Where should I put it? The three terms. Any question? Any ideas? Any answer from you guys? Volunteers? The question is, where should I put a t for the three terms on the right? If I want to say, just write it out. X transpose W, X transpose inverse. I'm trying to do this. Where should I put a t?
If the x's are fixed, then probably only w contains beta.
Yeah, that's correct. What is W? Even though we simplify notation, but let's come back to this, right? It's the variance of y1 to yn. So wi is the variance of yi. Variance of yi depends on the location parameter, right? Recall that. Variance of yi based on exponential family it's basically AI phi, which we don't worry about, it's fixed, times B double prime theta I. And if you recall, this theta I links to our parameters beta. So that's why this will be updated. So this one depends on the current parameter value. So beta will kick in here. And also G prime mu I. Mu I also is related to beta. So beta will influence both the theta I, therefore the variance of yi, and also the mu I. So therefore, and beta will also come into the mu I. So it will go into both terms. So that's why W depends on beta. And so if this is something you are not so, if you don't want to make any mistakes in your derivation, a good idea is to put beta here. So know you that it's W beta. W depends on beta. Okay, so coming back here, then the T should be put under W. Finally, last term, score function, which is here. Okay, and then I can give you the answer. As I said, mu depends on the beta, and this d eta d mu, this whole thing is yi minus mu I times g prime mu I. So mu I, they all depend on beta. So therefore, in the score function term, W and the last term, they both depend on beta. So they depend on iteration. All right, so I will put it here, X transpose WT. Finally, this interesting thing, I'll put a thing around it, y minus mu d eta d mu t. I call this whole thing. Okay, so that's basically it. So you see the similarity here is that we have X transpose WX inverse times X transpose W times something. And this is exactly the formula for weighted least square. And maybe I should tell you, I think we can talk about the weighted least square right now, because we basically covered the weight, because we basically covered the iteratively weighted least square. So this is the update rule. So then let's think about the weighted least square as how we can find the connection here. But before we move on that, I think I just want to summarize that everything we said so far is based on derivation. And what we aim to do is to maximize the log likelihood. And we want to use the Newton-Raphson algorithm, but Fisher simplified it to be the Fisher scoring algorithm. The key difference is that for the second order derivative matrix, we're not using the Hessian, we're using the expectation called Fisher information. And the Fisher information is expected negative Hessian of the log likelihood. Scoring function is just the gradient of the log likelihood. Because of the special property of exponential family that allowed us to simplify the gradient of the log likelihood score function and the Fisher information in a way so that we turned out to get a form like this. So now I will introduce the weighted least square, okay, as a side information, external information, so you can see the connection. So I'll put a question here, weighted least square. What is the weighted least square? This is for the problem of the linear model where our assumption is less constrained, less strict, called heteroscedasticity assumption. So in this case, we will modify our random structure. I like this formulation because it makes things clear. As yi still independent, normal distribution, mean mu I, but the variance is now specific to yi. So we have sigma I squared for yi. They're not all equal to sigma squared. And we still have the systematic structure as before. Mu I equals xi transpose beta. Same as before. And we just consider the very simple scenario when we consider this sigma 1 to sigma n to be known. Let's just do that. Yeah. So simple scenario is that sigma 1 squared to sigma n squared are known. Okay. Then we can show that the MLE, maximum likelihood estimation, we will have something interesting. Let me just first write down the likelihood for you. So, or maybe the log likelihood of beta. I will still just keep the major terms, I from 1 to n. After the log, everything, the exponential function is gone. Negative yi minus xi transpose beta squared to sigma I squared. That's it. So you see that we cannot cancel out everything plus some constant. Yeah, which is related to sigma I, but not beta. Once you take the derivative of beta, so one thing that's different from before is that the sigma I squared will stay. You cannot just cancel them because the other side is set to 0. Let me just say this. So when you set this partial, this, so previously, when you set this to 0, you can cancel the common sigma square from the denominator because it's the same term you can get out of the summation. But now you cannot do that. You have to keep them inside. So therefore, you see it becomes just sigma I squared is just 2 is gone, yi minus xi transpose beta. And we would also have xi, right? So basically, we would have yi, xi. We will have it like this. That's just our gradient. So xi is a p-dimensional vector, while yi is just a scalar. So we just have the gradient as this, and we want to set it to 0. And then you see the sigma I squared will stay. Or we can also use the matrix form to simplify things. So I will not talk about that because we can write on the matrix form. But basically, I can show that by setting this to 0, the beta hat MLE would turn out to be this form. X transpose W X inverse X transpose WY, where we just set W to be 1 over sigma 1 squared, 1 over sigma n squared, and other things are 0. So if I want to make a connection to what we have previously, each one is the variance of yi. So this is basically 1 over variance of y1, 1 over variance of yn. That's it. So to make the connection, you see, the only difference here is that we also have the variance of y1, variance of yn in our w, but we actually rescale the variance by g prime mu I squared. That's what we have. And also, if for some of you who might have learned about the delta method using statistics, this is very similar to the delta method. It's just like we are going to transform yi to something by function g. but we want to approximate the new variant, the variance of the new variable g of y1, yi. Then this is actually the delta method's approximate formula for the variance of g of yi. So we're basically doing that. So essentially, if you connect the W to this one and the formula to the formula here to this one, you see that it's almost the same thing, right? It's almost the same thing, except that our y in this update is not the original y, but this y. What this new thing? This new thing is what? Just to write it out. y1 minus mu1 g prime mu1 yn minus mu n g prime mu n. So it's the same thing. So what I'm saying here, this is also kind of like the delta method, which relies on Taylor expansion. So you are transforming y by g, but you are surrounding the mean of yi, which is mu I, surrounding the mean. You are using this linear approximation as a way. So basically this g prime is the slope, right? You're using this linear approximation to approximate the g of yi at mu I. I'm not sure if what I said makes sense to you, but I'm trying to give this kind level of intuition if you are familiar with delta method. But if not, you can ignore what I just said, because this is relying on some previous knowledge about delta method for approximating the mean, for approximating the variance. All right, so probably we will continue next time. So like I said, what I said to in the announcement on the Wednesday, I will first go over the homework solution and then play a video recording to continue from there. But before we end today, I want to just add a few notes about just the weighted least square on its own. So you see, this is the MLE for the weighted least square, but W depends on sigma 1 to sigma n square, but they're unknown, right? We're assuming they're known. If they're unknown, how would you calculate this W? So therefore, in practice, to solve the weighted least square, we need to be iterative. In practice, we start with just an identity matrix for W. Let's say start with W0 to be just the identity matrix N. Then we fit in each iteration, T. We use the current beta hat from the previous iteration as a way to do the prediction. So we will get y hat just as x beta hat t. Okay, and the x beta hat t is from the previous weighted least square or MLE formula. So you will get x transpose w t minus 1 from the previous iteration, or I'll just say t. I'll just say t for simplicity. X transpose times x inverse, right, times x transpose wt y. So this is how you get from the previous, from the current wt, and you get the current beta hat t. And then from here, you compute residual in this iteration as y minus y hat, also as y hat t. Right, and that will give you the residual. And then you update your W t plus 1 matrix as this. So you will define it as 1 over E t. So this is just, we have n entries of it. So I just call that ET1 to ETN, the n residuals. So I have ET1 squared to 1 over ETN squared. So basically, we're using the residual square for each observation as an approximate, as an estimate for its sigma I square. And that give me the new weights. So basically, what essentially happens in this weighted least square is that if an observation has a particularly large residual in the current iteration, then it will have a very small weight in the next iteration. So this weight will be very small, so it won't influence the beta hat estimate as much. So this is the weighted least square if you believe that heteroscedasticity is your concern. But as you can imagine, that this iterative algorithm will not give you a result as stable as just doing least square. So you must have some strong justification for doing so in practice. But that's why we didn't introduce this as a major method in this class. But on the other hand, I want to say that seeing the connection here with the reweighted least square is something very useful. So before we wrap up, I will say some last note about this reweighted least square. So that's what's called IRLS. Iterative, this is called reweighted least square. Why we call this algorithm iterative? It's obvious, right? We're updating beta iteratively. Reweighted means that this W weight is being updated. It's every time we reweight it. And at least square, LS is for least square. So in this case, you see that the intuition is that we're doing reweighted least square, weighted least square to estimate beta, not using the original y's, the y vector, because the yi's could be binary, could be count. They're not like the continuous response we have for Gaussian model. However, what we're doing here is that we subtract the mean and we multiply by this g function. Remember, g is the link function, and the link function is trying to map whatever range of the mu I to the real line range, the real values. So therefore, you can consider this to be a transformation of yi to be kind of like Gaussian random variable. So therefore, we're using these variables. I think they are called the how to say, it's called working variable. Yeah, there's a jargon, working variable instead of the original yi's to do the weighted least square. So you can imagine this is something we transform the yi into Gaussian-like and then treat it as a least square linear regression problem. So probably it's a little bit abstract today because we're just giving the general form, but I think things will be clearer once we come back. Once I think on Wednesday, you will see that we will give examples about doing the logistic regression and the Poisson regression. For specific examples, you'll see how this working variable is actually behaving like. And also, this is something you will be able to try in your next homework. So I think maybe the next homework, yeah. So that's what we'll have. So I think the idea is very general in that if you have some very useful tools for the simple scenario, then you can think about how can I convert my current scenario to the simple scenario, which is linear regression least square, to help us solve the problem. And another note is that this chain rule thing is essentially what's used in the back propagation algorithm for training a neural network, because it has so many parameters, so many layers, but essentially what's doing there is the gradient. You're trying to use the chain rule layer by layer. Okay, so I will stop here and I want to ask if you have any questions before we finish today.
Maybe just quickly, when you did the gradient for the weighted least squares, I think I was confused about one of the terms. It was like yi minus xi transpose beta times yi times xi.
Why? Can you say that again? Which
I think on the other paper.
the other? So are you seeing
Oh, yeah.
this one, right?
Yeah.
Yeah.
I think I was a little confused how the yi came out.
Xi transpose. Oh, I see. 2 times. Yeah, I think it was my bad. I don't think.
Oh, okay.
Yeah, sorry. Yeah. Okay.
Okay, thank you.
Thank you. Yeah. All right. So then I will see you next Monday. Thank you. Hopefully I can see you in person if I'm getting better. Bye. Bye, everyone. Bye.